Hello and welcome to the SigmaXL video tutorials. This video features the reliability Weibull analysis found on page 178 of the SigmaXL version 8 workbook. The Weibull distribution is a continuous distribution that was publicized by Weibull in 1951. It's become widely used, especially in the reliability field. The Weibull distribution's popularity resulted from its ability to be used with small sample sizes and its flexibility. It can also be used as an alternative to the Box-Cox transformation to determine process capability indices or control limits for non-normal data. Weibull is particularly effective when the data are censored, with exact failure times unknown, or suspension of test. Suspension of test is also referred to as write-censored. SigmaXL can analyze complete or write-censored data. For this video, we'll be using a sample dataset found in SigmaXL. To begin, click Help. Click Sample Data, and then select the file weibull.xlsx. This file contains write-censored time-to-failure data. Now let's analyze this data. Click SigmaXL, Reliability Weibull Analysis. Select Time to Fail on the left, and then click Numeric Response Y. Select Sensor Code. Click Write Sensor Column. The default sensor value of 1 will be used. For this example, we will use the default method of estimation, which is maximum likelihood. Note that some reliability practitioners prefer least squares regression X on Y for small sample sizes. Other defaults include threshold equals 0, confidence level equals 90%. In order to estimate survival probabilities, I'll have to enter the time value separated by a space. I use 10 to 100 in increments of 10, and 100 to 300 in increments of 50. Clicking OK will result in our Weibull analysis report. The Hollander-Prussian test is used when there are write-censored observations. If the p-value is less than 0.05, this indicates a significant lack of fit, so Weibull would not be an appropriate distribution. Given the p-value of 0.98, there is no lack of fit with this time-to-fail data. This is confirmed in the Weibull probability plot, with the data roughly following a straight line. If our data is uncensored, then the Anderson-Darling unadjusted test would be used. The shape parameter, also referred to as beta, is the slope of the line on the Weibull probability plot. The Weibull distribution can be used in a wide variety of situations, and dependent on the value of beta, is equal to or can approximate several other distributions. For example, if beta equals 1, the Weibull distribution is identical to the exponential distribution. If beta equals 2.5, the Weibull distribution approximates the log normal distribution. And if beta is 3.6, the Weibull distribution approximates the normal distribution. Because of this flexibility, there are few observed failure rates that cannot be accurately modeled by the Weibull distribution. Furthermore, if beta is less than 1, the system is suffering from infant mortality failures. If beta equals 1, failures are random. They are occurring at a constant failure rate and are independent of time. If beta is greater than 1, components are wearing out with age. The scale parameter is the characteristic life. This is the point at which we could expect 63.2% of the population under study to have failed. The survival probability report shows that the survival probability at the time 200 equals 0.386. So, the cumulative failure probability at 200 is 1 minus 0.386 equals 0.614. The percentile report tells us that we can expect a 50% failure rate, or 1/2 the population will fail, at 179.73. This is the median. The percentile report can also be used to determine control limits for non-normal data. The lower control limit is the 0.135% value, which is 22, The center line is the 50% value, 179.73 as mentioned before, and the upper control limit is the 99.865% value, which is 383.5. This concludes the SigmaXL Reliability Weibull Analysis tutorial video. For more tutorial videos, go to sigmaxl.com/web_demo.shtml or come join us at our YouTube channel at youtube.com/SigmaXL Inc. Thank you for joining me.